Hello, Chem 1A. This is Chapter 12, Lecture Video 3, and we're going to discuss enthalpies of hydration and summarize our intermolecular forces, and then finally do an example problem for intermolecular force strength. So, what are enthalpies of hydration? Now, they are somewhat related to our ion-dipole interaction. An enthalpy of hydration is defined as the amount of heat given off when a gaseous metal ion is hydrated by water. So, for instance, lithium plus gas going to lithium plus aqueous. They are pretty much always going to be negative, as you can kind of see here. And this isn't going to have a lot of effect on the material we're covering in this chapter, but it will be referenced in our next chapter's material. So just kind of keep in the back of your mind. Now, one trend for this, as you can kind of see, is that as our size of our ion gets bigger, the enthalpy of hydration gets less negative or smaller, but always negative. So yeah. So let's summarize our intermolecular forces. If you have a particle interacting with another particle, you should ask yourself really a couple questions here to figure out what intermolecular forces are present. For instance, are ions involved? Most often, I'm going to tell you right now, 99% of the time, you're going to say, no ions involved. So the next important question here is going to be, hey, are polar molecules involved? If the answer to that is no, cool, then there's only one intermolecular force present. It's London dispersion. That's it. When you answer no to here. However, if you answered yes, there are polar molecules involved, then we need to ask ourselves one more question. Are there hydrogen atoms bonded directly to a nitrogen, oxygen, and fluorine? And if the answer to that is no, then you have both London dispersion and dipole-dipole interaction present. If the answer to that was yes, that's not a good color, then you have hydrogen bonding, you have dipole-dipole, and you have London dispersion present. And these are the main three. These are what most things are going to have. You don't really see very often any ion-dipole interaction. However, let's go back to the very beginning. Let's say, hey, yeah, right here, that wasn't a no, that was a yes. Then you need to ask yourself, are there polar molecules involved again? And if the answer is yes, then you have ion-dipole, you definitely have dipole-dipole, you definitely have London dispersion, you maybe have hydrogen bonding present. It might be, it might not. It depends on if this guy actually is true, right? If you have hydrogens attached to oxygen, nitrogen, or fluorine. If the answer is no, well, then you don't really have ion-dipole. You just have ionic bonding occurring, and we're really not looking at intermolecular forces in general. So this one's not really a relevant answer. Okay, so let's put this into practice. I want to determine what types of intermolecular forces are present for each of these molecules. And I want to put them in order of increasing intermolecular force strength. So, first off, let's look at this guy. Now, this molecule we know has London dispersion because everything has London dispersion. Because of this OH group here, I know this is going to be a polar molecule. And if we draw out the Lewis structure, we'll be able to see that due to its asymmetry. So it has dipole-dipole interaction. Also, because I have this oxygen-hydrogen bond here, I know I also have hydrogen bonding. And we can see that when we draw this Lewis structure out. So let's do that. Let's draw this Lewis structure out. Okay, so here's our Lewis structure for CH3CH2CH2OH. You can see that we have this OH bond here that gives us the hydrogen bonding. Overall, the molecule is mostly asymmetric with the oxygen pulling electrons towards this way, so it is polar and has a permanent dipole moment, and that's why we see these three types of intermolecular forces. Now, if we draw this guy's Lewis structure, we get a structure that looks very similar. It's just one CH2 group less. So we're going to have similar types of intermolecular forces. We're going to have London dispersion because everything has that. It's definitely still polar. This is ethanol, the alcohol present in alcohol beverages. So because it's polar, it has dipole-dipole. And we have, again, that OH group here. So there's an oxygen bonded to a hydrogen. We have hydrogen bonding as well. Okay, so now if we look at the other ones, we can draw their Lewis structures as well. And now that we have those Lewis structures drawn, we can see that since I2 is a nonpolar molecule, it's only really going to have London dispersion, and that's it. Oxygen is also a nonpolar molecule, O2, because we have no electronegativity difference between the two elements, so it's just going to have London dispersion. BF3 is a trigonal-planar molecule. It's completely symmetrical, and even though we have polar covalent bonds in this compound, because of its high symmetry, it also is going to be nonpolar, which means it only has London dispersion strength, or London dispersion in its intermolecular forces. Okay, so now let's look at how these different molecules would arrange themselves in terms of intermolecular force strength. So let's say we are going to go increasing IMF strength this way. Now, the ones with London dispersion, they seem to be all tied because they all have the same type of intermolecular force, and as we know, London dispersion is the weakest intermolecular force. However, if you remember from our slide in the last lecture video where we talked about London dispersion, you know that London dispersion strength actually increases with increasing molar mass. So let's calculate the molar masses of our three molecules that have London dispersion as their only intermolecular force. Okay, so calculating out our molar masses, for I2 we get 253.8 grams per mole, O2 we get 32, pretty much even, grams per mole, and BF3 we get 67.8 grams per mole. So because of this, our lowest molar mass is going to be our weakest London dispersion. So that means O2 is our first molecule here in terms of increasing intermolecular force strength. Then comes BF3. And then comes I2. And this is pretty much how we always settle ties of the types of intermolecular forces present. So if two molecules have the same types of intermolecular forces, the one with the larger molar mass will be stronger due to increasing intermolecular force strength. As a general rule, dipole-dipole, hydrogen bonding, these two don't really change in strength too much between different molecules for the most part. And so London dispersion is pretty much always going to be the tiebreaker. This brings us to our last two molecules here. Both of these two molecules up top, our first two, have the same intermolecular forces again. So again, we need to calculate our molar mass of the two, compare them, and then put them in order based on increasing molar mass due to increasing London dispersion strength. Okay, so having calculated our two molar masses, the molar mass of our first molecule here, which is actually propanol, is 60.11 grams per mole, and ethanol is 46.08 grams per mole. I don't need you to know the names of these compounds. This is something you'll learn at the end of Chem 1B and mostly in organic chemistry if you need to take those courses. So because the molar mass of CH3CH2OH is smaller, it's the next one in terms of strength. And then our final and strongest one is CH3CH2CH2OH. And so this gives us an example of how we can put different molecules in order of increasing intermolecular force strength. This is very important to the next part of this chapter where we talk about how intermolecular force strength is going to affect our bulk properties like boiling point, vapor pressure, viscosity, and so on. All right, if you have any questions, please do not hesitate to reach out. I'm there for you if you need help.